Hello, hi guys, welcome back to my channel. From the previous chapter, in chapter 1, you already learned all about big data, from its definition, concept, and everything. Now we're going to continue our lesson in chapter 2, all about big data processing architectures. So here is the contents for these chapters. We're going to have 6 subchapters. We started with the data processing revisited, and then data processing techniques, and then data processing infrastructure challenges. Next one will be the architecture. There are 2 architectures, which is shared everything and shared nothing architectures. Then we'll go to the big data processing. Before we end with this chapter with a case study on the telco big data. Okay, now we're going to start with 2.1 data processing revisited. Okay, first, before we want to study the processing in big data, we must understand the processing in data as general first. Okay, let's look by definition what is data processing. Okay, here it is defined as a collection. We start with the collecting data, then processing and management, and lastly generate the information to the end customers. Mostly the data started with the collection. The data can be collected from anywhere, any system, any form or any portals. Then all the data collection will go through the process in a sort of classify, transform, sort, calculation, summarize, all that kind of process. Okay, feature extraction, feature visualization, that's a part of processing data also. And then after we process the data, we want to manage the data. By manage, we want to put it in storage, or archive, or retrieval, or governance. And lastly, after we manage the data, we're going to generate the data in terms of presentation for the end customers to understand what the data we collected at the first place. Okay, all this all these cycles can be seen in this figure. Okay, that's what actually I'm talking about. Okay, now based on the figure in the cycle as shown in the previous slide, the transactional data processing also follow the same life cycle as the data is first analyzed and then modeled. It also same with the data warehouse data processing as it follows a similar pattern with transactional data processing. So that means the cycle is same with transactional data processing and also with data warehouse data processing. Okay, except the key difference is the volume of data to be processed varies in this data warehouse for data processing. Okay, the data collected in transactional data processing usually in a structured in nature and discrete in volume, since the entire process is predefined based on known requirements. Other areas of data management like quality and cleansing are a non-issue as they are handled in the source system as a part of the process. Okay, before we move into the big data processing, we should discuss the techniques and challenges in data processing in the next slide. Okay, this is the hierarchy of data processing technique. Okay, data processing is divided by 2, which is centralized processing and distributed processing. It is same like analogy like aircon. Aircon we have the centralized and distributed. So same analogy. Centralized, that means it's focused on the one center only, while distributed is the data distributed to certain portion. Okay, there are 5 processing and distributed, which is client server, 3-tier architecture, n-tier architecture, cluster architecture, and then lastly is peer-to-peer architecture. Okay, we're going to go one by one. What is centralized processing and distributed processing first before we go to details in the distributed processing. Okay, first for the centralized processing. Okay, in this centralized processing, the architecture, the data is collected into the single centralized storage. Like I said, the easy analogy that you can see is like the centralized aircon. So you can see in one aircon in the mall. So it's same with the processing. There is a one single centralized storage, and this storage will be processed by a single computer, but often very large architectures in terms of memory, processor, and storage. Because it only has one single computer, that means the storage, memory, and processor has to be very large. Okay, centralized processing evolved with transaction processing and are well suited for small organization with one location or service. So it is not suitable for big organization. It's only suitable for small organization, because if big organization, they have a very huge data and we cannot depend on one single computer only. And then centralized processing requires minimal resources from both people and system perspective, which is it suits the small organization. Okay, because the resources is very minimal. And then centralized processing is very successful when the collection and consumption of data occurs at the same location. Right? For distributed processing, is a there's a lot of types. It's much more complicated than centralized. Centralized is more easier to understand. For distributed processing, in this architecture, data is processing are distributed across geographic or data center, and processing of data is localized with the federation of the result into a centralized storage. That means there's a lot of computer, and then the computer will storage in the data center, and then it will be go to the one centralized storage. Okay. Okay, distributed architecture evolved to overcome the limitation of the centralized processing, because centralized processing it only support the small. It's okay for the small company, but if there is a very big company or um, big organization, they cannot use the centralized, so they have to use this distributed processing. That's mean distributed processing is introduced to overcome the limitation of centralized processing. Okay. Alright, from distributed data processing, first we have the client server. This is a very old one. This is processing started in 1980s. This most popular method. I think some companies in this era still use it, this client server, but not much, because the client server has evolved to three-tier architecture. Okay, but first we focus on this one. Client server is like a relationship where the client does all the data collection and presentation, while the server does the processing and management of data. So it's like a two relationship here, only client and server. While three tiers architecture is the upgraded from the client server to increase the processing efficiency and reduce latency while increasing reusability. So it is an evolution from the client server architecture. Okay, whereas the client processing logic was moved to a middle tier of service, thereby freeing the client from having to be tethered to the server. So this processing techniques is introduced to um, reduce the burden of the client. So it has a middle person here, not just client and server. It is another middle person that going to help the client doing this work. Okay, this evolution allows scalability of each layer, but the overall connectedness of the different layers limited the performance of the overall system. This is predominantly the architecture of analytical and business intelligence application. Most of the company that use client server has upgraded through this three-tier architecture lah. Not much company nowadays use only client server. I think it's if the company is a small company, it can use client server, and if it is big company, big organization, is better for to use a three-tier architecture. And then we have an NT architecture. which is upgraded from the 3 tier. N-tier, that means it has more than 3 tiers. Okay, it has a clients, middleware, application, and servers in one tier. So first we have client server, then we have a middleware, then now we have the clients, middleware, application, and server. There's more than 3. Okay, by this architecture, any tier can be scale independent of the others. Web application use this type of architecture approach. The next one, we have cluster architecture, which is refers to machines that are connected in network architecture. Network architecture is a software or hardware to closely work together to process data or compute requirements in parallel. Okay, if before this we have the N-tier, which is work in the web application. Okay, for the cluster architecture is related to machines that are connected to software or hardware. Each machine is in a cluster is associated with the task that is processed locally, and the result sets are collected to a master server that returns it back to the user. So it's like an online software. I think it's very easy to relate it. It's a software because software like for example Hadoop, okay, is software. Okay, it has a connection between the data that we process through the software, and then the machine processes data locally, and then the result can collected to a master server that return back to the user. The user will get back whatever it want to analyze, or maybe you can see another software that you usually use, like MATLAB or SPSS that you use to generate the outcome from the whatever input or whatever data you use in that software. Okay, lastly, we have the peer-to-peer architecture. This is a type of architecture where there are no dedicated servers and clients. Instead, all the processing responsibility are allocated among all machines, known as peers. So this is a very different architecture compared to this for previously processing technique. Okay, each machine can perform the role of a client or server or just process data. So it's not depend on client, it's not depend on server, it is the machine itself. So the machine doing all that lah. And that machine like peer-to-peer is like a friends. Okay, we friends, so we perform everything by our own. So we don't um, just depends on other person, so we can do it all, but we have another friend, another machine, which is our peer-to-peer architecture. That's what a peer-to-peer architecture means. Okay, it is very easy to understand here. Okay, peer-to-peer is not related to the other four. The other four is related especially client server, how it evolved to 3-tier, and how 3-tier evolved to N-tier, and lastly the cluster architecture. Okay, on to the next slide, which is the advantages of distributed processing. There are 3. First one is scalability of system resources can be achieved based on isolated needs. Second, processing and management of information can be architected based on a desired unified operation. And then the last one, parallel processing of data, reducing time latencies. So it saves you a lot more time than using the centralized. Okay, because we don't have to depend on one single machine only. However, there are not all good things about the distributed processing. There are also some disadvantages of distributed processing, which are therefore here. First, data redundancy. Second, process redundancy. Third, resource overhead. And fourth is volume. Okay, let's say take one example here, like process redundancy. Okay, since distributed processing is sometimes it can be parallel, so the first machine and second machine can do the same process, same things. So that's what it mean by the process redundancy, because it has this we don't know what the machine one do, we don't know what the second machine do. It can be the same task that the machine are doing, so it is what we call as a process redundancy. Here are the most popular distributed processing implementation in the data world. There are three: peer-to-peer, hub and spoke, and federated. However, I only explained to you peer-to-peer. In this course, I didn't explain hub and spoke and federated, but you can Google that. Okay, processing data in IDEA, the centralized processing or distributed processing style has a lot of infrastructure challenges that continue to dominate the space. That means there are a lot of challenges of data processing. Okay, we're going to discuss here. Okay, in this, before we discuss what is the challenges faced by data processing infrastructure, first, this figure, okay, it shows the computational units of data processing, which is a computational unit that has remained the same from the days of punch card to modern computing architecture. That means this architecture has never been changed. Okay, from the the punch card that you use, if you ever worked before to start a work, so you had used punch card, but nowadays people like using thumbprint or probably just key in into the my work here. Just go to the website and key in, check in through the website. Okay, maybe different places has different technologies in collecting data of the attendance. Okay, but the point is the architecture here had been same for during that in 1980s until modern computing architecture until now. Okay, so since the processing architecture is being the same, there is a lot of challenges that we need to face lah. Okay, there are storage, transportation, processing, and also the last one is speed. So we're going to discuss all these four challenges. Okay, we're going to start with storage first. Okay, what is the challenges that we face with the storage? Okay, because now we have a very huge volume of data. The amount of data that needed have been increased. So it's not that you can use the same storage like you used in the 1980s. Okay, for example, we have the sensor to collect the data every minute. Even if the data is collected every 1 minute, 15 minutes, the data uh, will be very big. If you counted, let's say the data is collected in interval time 5 minutes, in 60 minutes, in 1 hour, it can be that already has a huge volume of data. Okay, that means we need a proper storage. We need the bigger storage to store that data. Okay. Okay, storage has been a problem in the world of transaction processing and data warehousing, especially now that we have to deal with a lot bigger, not just sensor, it's also storage within the data social media, within the website, within the ClickStream, all that sources that you already learned in the chapter 1. Okay, all the data that need to be stored. So storage has been always a problem for the data warehousing and big data. Okay, due to the design of the underlying software, we do not consume all the storage that is available on this. Another problem with storage is the cost per byte. Okay, it's very expensive. So even you can see for your Apple, I think if you use iPhone, you have not enough storage in your phone, so that you have to store your pictures or your whatever you have inside your phone through the cloud. Okay, and the cloud is not free. You have to pay like RM3.90 for very minimal storage. And if you want a bigger storage, you have to pay more. That means it's costing. Okay, storage is not free. So every little storage will cost you money. So it just depends. Just imagine. Okay, the storage that you need for the huge volume of data that very costly for company lah, for social media company, for anything company that involving with the data collection. Okay, very easy to understand the challenges in the storage. Okay, next is transportation. It is also the one of the biggest issue in the data. Okay, as data, you need to move the data between different system. Okay, that's what I mean by transportation. Okay, data is not just stay at the same place. Okay, you maybe have to use the data in different software, or then you want to store it, loading in memory for manipulation is involving the data analysis. Okay, we have to transport the data to the other system. Okay. This continuous movement of data has been one of the reasons that structured data processing evolved to be recursive in nature, where the data had to be transported between the compute and storage layers. The continuous improvement in network technologies could not solve the problem, though it enabled the bandwidth of the transport layers to be much bigger and more scalable. Okay, which mean this evolution of the movement it's been reason why the such data is evolved. Okay, there are very many layers in the data transportation, not just one layer. Okay, I think if you study the data structure before this, you will understand how the data transport from one system to another system. Okay, that's another challenges that we have to face. Okay, the next one is processing. Okay, processing involve these three: CPU or processor, software, and memory. Okay, for CPU, processor different computer has different speed. Okay, not everyone can afford i5. Um, if you have like very uh, I mean recent CPU, okay, you have a i7, okay, and your friend have only can afford i5. So different computer has a different speed and different processing. Not every computer has the same CPU or same processing. Not everyone can afford an i7. Okay, that means the different processing or different type of speed here. Okay, leading to more processing capabilities, access to wider memory, and have facilitated architecture evolution within the software layers. Okay, that's what I'm trying to say here. Okay, the different generation of computer has a different speed and different processing. Okay, for software, also different software has different operating system and programming language. Okay, not every software is same. Like Python and R is a totally different software. Okay, in its lowest form, the software translates sequence instructions set into machine language that is used to process data with instructions layers of CPU plus memory plus storage. Programming language that have evolved over time have harvested infrastructure evolution to improve the speed and scalability of the system. For example, like previously we have the C. Okay, that is very basic of programming languages. Then C has been evolved to Java, and then it has been evolved to Python. So Python now is the evolution of this basic programming. It become easier for the user. Okay, the evolution of the software here, we can see it will be challenges uh, for data process lah. Okay. Also, beside the different programming language, you can see the operating system. Okay, different operating system like Linux or Windows. Okay, there are two different um, operating system here. Okay, like Linux, they have opened the doors of innovation to enterprises to develop additional capabilities to this software platform for leveraging the entire infrastructure and processing architecture improvement. Okay, that is Linux. There is a lot of improvement in Linux, but not many people that use it. Most of people that use Linux probably from IT. For the end user, we usually use the um, Windows, which we just use the system without know how to, that's why I think a window does not open the door for innovation, and that's only done by Linux. Okay, the third one is memory. Memory has become cheaper and faster, which is, in the old time, okay, during back my days, when I want to buy the even pen drive, okay, pen drive 8 gig is very expensive. But now it's just like cost you like um 11 is 16 ringgit, which is compared to during our time, it can be as expensive as 60, 50. Okay, it has become more cheaper and also faster. Okay, now we already have 1 tera, 2 tera. Okay, it's more bigger storage and more cheaper storage. Okay, with the evolution of processor capability, the amount of memory that can be allocated to a system then to a process within a system has changed significantly. So all these three, CPU, software, memory, all these are involving in the processing. Okay, how the evolution of these three has been the challenges, okay, for data processing. Okay, lastly is a speed or throughput. Okay, speed is the biggest continuing challenge, okay, in data processing. Speed is a combination of various architecture layers, hardware, software, networking, and storage. Is not only one. Okay, it's involving all this combination of architecture. Okay, each layer has its own limitation. The hardware has a different speed. Okay, software has different speed, network also has different speed, and storage also has a different speed. And then the combination of these four, these very different architecture will has a limitation. Okay, this will be challenged to process the data. Okay, let's say you have a hardware that is very fast, okay, also very fast software like Python, but your network is not so good. You have a network connection problem, and it will be a limitation for you to process the data. Okay, let's say another example, you have a very good hardware, very good software, and you has a very network, that your network has no problem, is very fast, but you has no storage, so it's also a limitation. If you have one limitation of one of these, that means the data will be take a longer time to process. So this it means by the speed um, challenges in data processing. Okay, it is the biggest because it's a combination of these four instead of one only, right? Now I'm going to explain about the shared everything and shared nothing architecture. Why we have to know this? Because data processing is an intense workload that can either scale dramatically or severely underperform and crash. The key here, we have to know which the right architecture to be used to process our data. Okay, there are two popular data processing infrastructure architectures. In here, I'm going to explain to you which first one, shared everything, and the second one is a shared nothing architectures. Okay, we start with the shared everything, which are the architecture that's suited for applications, for apps, and meanwhile the shared nothing is suited for the data warehouse and web application. Okay, I'm going to explain the shared nothing later on. Okay, we just focus on the shared everything first. Shared everything is the everything like memory, storage, processor, all these kind of resources are shared between the network. Okay, it is the most architecture that been used. Okay, it based on the nature of the data and the type processing. Okay, I'm going to show you the architecture, the figure later on. Okay, there are two variations of shared everything architecture, which I'm going to explain later more about the symmetric multiprocessing, which is short for SMP, and distributed shared memory and DSM. Okay, it is the explanation is on the next slide. Okay, because the advantages of this architecture is the limited scalability. The drawback will be explained in the next slide too. Okay, the drawback of the uh, shared everything architecture and those involving SMP and DSM2. Okay, for the shared nothing, okay, already told you that is already that is suited for data warehouse and web application. It is has a different system that where multiple system called which is known as also as nodes to form a scalable system. That means it's more scalability than the shared everything. It is advantages. Okay, the nodes is not uh, has a very own private memory, disk and storage devices is very independent. It does not depends on the whole. It does not share everything. It's very independent. So the nodes will is carry on private memory, and also it's has a different task. It is a system where it is dedicated application or partition its data among different nodes to handle particular task. That means it doesn't share anything. Obviously, it is carrying its own responsibility. Everything is by its own. Okay. It enables the creation of self-contained architecture where the infrastructure and the data coexist in a dedicated layer. Okay. More on the shared everything architecture compared to shared nothing. So I'm going just to elaborate more about the shared everything architecture. There are two different already explained to you in the previous slide. There are two different types of shared everything architecture. First one is SMP, second one is DSM. So we start with the SMP architecture first. In the SMP architecture, all the processes share a single pool of memory for read-write access concurrently and uniformly without latency. Sometimes this is referred to as uniform memory access, which short as a UMA architecture, but there is drawback here. The drawback of this SMP architecture is when multiple processes are present and share a single system bus, which result in choking of the bandwidth for simultaneous memory access. Therefore, the scalability of such system is very limited. Okay, the scalability already explained to you. It is the advantages of the shared everything architecture. But in the SMP architecture, it happens in this way. When the multiple processor, so it has a single system bus and it has to do everything, but the system does not capable to do it everything. So it has start with the memory access, then you cannot use it. That's is the drawback of the architecture. Okay. For the DSM architecture, it's addressed the scalability problem. Okay, the scalability that already explained to you in the SMP architecture. So they introduced this DSM architecture. Okay, it solved this scalability problem by providing multiple pools of memory for processor to use. In this architecture, the latency to access memory depends on the relative distances of the processors and their dedicated memory pools. This architecture is also referred to as non-uniform memory access, which is short for NUMA architecture. Both are the architectures they are complement to each other, which DSM is better than SMP. Technically, DSM is introduced to cover the disadvantages of SMP architecture. Okay, but both of these architecture have been employed for many transaction processing systems, where the transaction data is small in size and has a short bus cycle of resource requirements. That means can only process a very small transaction data. Okay, you cannot process a big data. The data warehouses have been deployed on the shared everything architecture for many years due to their in intrinsic architecture limitation. The direct impact has been on cost and performance. Okay, basically, data warehouse use this shared everything architecture, but the shared everything architecture cannot be used on the big data and analytical application because as I can say, as I already said to you earlier, it only can process the small data. Okay, next slide I'm going to show you the figure of the shared everything architecture. As you can see in the figure, everything is being shared, start from memory, processor, and the storage. Okay, while this one is a shared nothing architecture, okay, it interconnected within the layer, but it is the nodes. Okay, see there are different nodes here. See on its own. Okay, doesn't share the memory, doesn't share the this storage. Okay, it's just interconnected, but it is on its own. Okay, doesn't share the storage everything. Okay, so it doesn't share lah. There are two architectures. They are designed and deployed on share everything architectures, which are OLTP. OLTP stands for online transaction processing, and the second one is the data housing, the data warehouse processing. Okay, for the data warehouse, it is architected to be the enterprise version of the truth and the data repository for the enterprise. It is used for in the case of transactional data, where the structure and the volume of data are finite to be extend that shared everything architecture based database solutions satisfy the user needs for the performance, throughput, and storage while keeping a reasonable cost. It is already explained to you in the previous chapter, previous slide, where the data involving the shared everything is only small data, and that means the data is the volume is finite. Okay, with all the data from transactional system to a third party and other data being processed into the data warehouse, and downstream reporting and analytic application demanding access to data on a continuous basis. A shared everything architecture does not lend itself to meet the data volume, user demand, and total cost. The shared nothing data warehouse architecture, like a data warehouse application, is better suited for processing data in data warehouse environment. That means with all this complicated process, okay, shared everything architecture is not suitable for data warehouse. So it is more suitable to use shared nothing architectures in the data warehouse rather than use shared everything. Okay, for this side, we're going to explain more about the big data processing. Previously, we only basically just explained about the data processing. Now we more focus on the big data. Okay, there are four process which are same with the big data criteria. Big data criteria has 4 P's. Okay, and this big data processing also involving the criteria and aspect. Okay, we're going to look at the data volume, data variety, data ambiguity, and data velocity. Okay, for the data volume, it is involving volume. Okay, that means it's involving the amount of data that generated every day, every minute, every second. Okay, within or outside the organization. Okay, how big, how large the data is. Okay, but for the standard data, it includes memo, contracts, analysis, reports, everything. Okay, for standard data, it includes the articles, video, blogs, reviews, forums, social media, and mobile data. It is considered as external data. For data variety, you already know the variety is a different format. So same with data processing. Data variety is a different format of data that generated by different sources. For example, Excel spreadsheets, okay, and the associated formulas, documents, blogs and microblog, videos, images, audio, multilingual data, mobile sensor, and so on. Okay, then we have data ambiguity, the complexity of the data and the ambiguity associated with it in terms of metadata and granularity. So the example such as CSV, common separated values from the Excel. Okay, there is different type of format for CSV and normal Excel. Okay, Word documents have multiple formats. Sensor data from mobile versus RFID networks, microblog data from Twitter versus data from Facebook. That means different platform like Twitter has a different complexity of data. Okay, for the last one, which is data velocity, the speed of the data generation. Okay, different things has a different speed lah. Like sensor network, mobile devices, social media, YouTube broadcast, everything. And this is kind of example that has a different speed of data generation. Okay, social media maybe has a very high speed. Okay, while the other maybe not so like patient networks. Okay, this is a variety of the data generation that needs high speed in processing. Okay, due to the very characteristics of big data, processing data of different types and volume on traditional architecture like symmetric multiprocessing for short SMP, or massive parallel processing MPP platform, which are more transaction prone and disk-oriented, cannot provide the required scalability, throughput, and flexibility. The biggest problem with big data is its uncertainty, and the biggest advantage of big data is its non-relational format. Okay, this is the big data processing cycle. You can see the difference between data processing and big data processing. There is one more process here, the additional process, which is discovered. Okay, collect, process, manage, and generate. These four process in the data processing, but with data, the difference is that this has another process which is discovered. For this slide, I'm going to explain more about the data processing architecture requirements and infrastructure requirement. For data processing architecture requirements, there are 8 requirements, which all the details I'm going to explain in the next slide. Okay, there are 8. First, model-less. Second, near real-time data collection. Third is micro batch. Fourth is minimal data transformation. Fifth, efficient data reads. Sixth, multi-partition capability, and then store result in file system or DBMS, not rational. And lastly, share data across multiple processing points. Okay, all these we're going to discuss in the details later. For the infrastructure, there are 7 requirements which I'm going to explain in the next slide also. This is the big data processing flow. It starts with the gather data, and then in the landing zone, and then we load data, the ingestion, and then we transform data at the process and discovered stage, and lastly we extract the data. Okay, by extraction data, we do the analytic, deep integration, operational reporting, and raw data extracts. Okay, I'm going to explain to you the one by one. Okay, the data, load data, transform data, extract data, process. First one is gather data. In this stage, the data is received from different resources and loaded to a file system called the landing zone or landing area. Okay, that means we gather the data. But technically, we just collect data and gather in one place. Okay, and then its data is sorted into the subdirectories based on the data type. Any file modification like naming or extension changes can be completed in this stage. So you can just modify the file like name or change something. Okay, you can do it in this stage. Okay, next stage is load data. The data will be loaded after it's gathered. It's going to be loaded to the with the application, okay, of metadata. Okay, and then it's ready for the transformation. Okay, the loading process break down the large input into small chunk of files. So that means we have a large data. The data will be loaded into the very small data. But a catalog of the file is created and the associated metadata of the catalog is processed for that file. In this stage, one can also partition data horizontally or vertically depending on the user and processing requirements. So it's up to you whether you want to partition data horizontal or vertically. The next stage is transform the data. After we gather, load, and we might want to transform the data by applying business rules and processing the contents. This stage has multiple steps to execute and can quickly become complex to manage. The processing steps at each stage produce intermediate result that can be stored for later examination. The result from this stage typically are a few keys of metadata associated matrix. Okay, last stage is extract data. After we transform it, we want to extract it. Okay, this is more to the result. Okay, result data can be extracted for further processing, including analytic, operational reporting, data warehouse integration, and visualization process. So if you want to do the visualization, you can just extract data and visualize by using software like Excel or Tableau or so on. For the infrastructure, I'm going to explain here. There are 7, 8. There are more actually on the next slide. Okay. First, I'm going to explain about the Linux scalability. Okay. In this earlier this chapter, earlier this slide, we already discussed what is challenges for data processing infrastructure in terms of storage, memory, processor, and speed. Okay. In the traditional system, when you add the additional infrastructure, you achieve scalability, but it's not 100% linear, and therefore it becomes expensive. Okay, for example, when you add 1 terabyte storage, you get about half of the usable space with a RAID 5 configuration. But it's not going to happen in the case of big data lah, because there is already inherent design to accommodate for the scalability of processing. And therefore, the storage management architecture of traditional data management techniques are obsolete. So it's not valid for the big data processing. There is no such problem of storage and memory and processor lah. These architectures largely have been developed based on Google's original paper, which we're going to discuss more about the Google's original paper in the next chapter, in the next video. Okay, not in this one. Okay, our storage and index management technique. So it's already been solved by Google. The second one is high throughput or high speed. A big data velocity mandates that data be ingested and processed at high speed. This requires an infrastructure that is extremely fast across input or output, processing and storage. We need the high speed to process all this big data. Okay, the third one is fault tolerance. Big data, because of its inherent complexity, needs a fault-tolerant architecture. Any one portion of the processing architecture should be able to take over and resume processing from the point of failure in any other part of system. So it should be a fault-tolerant architecture. It cannot afford any point of failure, okay, in the system. Okay, that means by the fault tolerance. Okay, the next one, continue. The auto recovery. The processing architecture should be self-managing and recover from failure without manual intervention. So we need the auto recovery mode. And then programming language interface. Big data can be processed for multiple business scenarios. For example, a document can be processed for multiple subject areas and classified under more than one category of product or service. This processing cannot be done using any COTS, which stands for Commercial Off-the-Shelf Software, and needs custom coding and development. Okay, so it should be multiple business scenario. It cannot be one only. Okay, it has a multiple subject area and can be done by using more software. Okay, so they cannot be done by using one software only. Okay, next one is high degree of parallelism. By processing data in parallel, we can distribute the load across multiple machines, each having its own copy of the same data but processing a different program. Then the last one is distributed data processing. Okay, since big data processing happens on a file-based architecture, to achieve extreme scalability, the underlying platform must be able to process distributed data. This is an overlap requirement with parallel processing, but difference in the fact that parallelism can exist within multiple layers of the architecture stack. So it has to be parallel. Okay, in order to perform this to achieve the extreme scalability. Okay. The next one, we're going to explain on the data processing. There are 8 data processing explained here. Data model-less architecture, near real-time data collection, micro-batch processing, minimal data transformation, efficient data reads, multi-partition capability, store result in file system or DBMS, and lastly share data across multiple processing points. Okay, what I'm going to explain here how the data going to process. Okay, data will be model-less architecture because of the complexity of the size of the data. Because of the size of data, it's become more complex. Okay, that means no fixed data model when you process the big data. Okay, it should model-less. Okay, in other words, the data processing is on a schema-less, okay, and non-structured data set. Okay, it has to be near real-time data collection or real-time. It cannot be since it's a real-time or near real-time data. So to process this data effectively, a highly scalable and performing storage platform is needed. Okay, and then in the big data, it can be processed as real time. Okay, I already told you that. So we need it has to be processed as micro batch. Okay. Minimal data transformation. Big data processed with programming language provide for some transformation. Most transformation are executed as a multi-step derivation, and complexity is kept to a minimal within each step. So that means the transformation has to be made as minimal as it can. Okay, because it needs this one to improve the speed and design fault tolerance. If the processing is not minimal, then the feature of fault tolerance might be not achieved. Okay, efficient data reads. The data processing design should be read oriented, as there is no schema-based processing of data. Then multi-partition capability. The data processing architecture should be able to support vertical and horizontal partition of the data. Due to the size and the volume of data, both the partitioning technique will be implemented in the processing workflow. Okay, and then the result should be processed and should be stored. Process is file-based, and then the result should be stored in DBMS platform. Okay, not RDMS. RDBMS is DBMS. Okay, lastly, the replication and sharing of data is key processing requirement. The reason for this include the design of fault tolerant, multi-step processing and multi-partitioning. So it has to be, can be shared, the data can be shared across multiple processing points. Okay, in a nutshell, big data processing can be summarized as a file system-based, scalable, and distributed data processing architecture designed and deployed on a high-performance and scalable infrastructure. But this architecture is not fixed. Only the one size, not fixed, is not a one size fits all architecture. Okay, already show in this architecture, this conceptual big data processing platform. Okay, each processing layer within the architecture has at least several solutions and techniques that can be implemented to create a robust environment. Each solution has its own advantages and disadvantages for a particular workload. This will be discussed later lah. Okay, to understand the big data situation, we will going to discuss the telco organization, how they manage the requirement to create a robust architecture for data management. Okay, that will be explained on the next slide. Now we're going to look at the application in big data. Okay, the application that we're going to take a look is a telecommunication company, which are short for telco. Okay, in Malaysia, there are a few telco. You already know, you use your mobile network, such as Maxis, Celcom, Umobile, and others. There are a large telco company nowadays. They keep expanding. Okay, let's say we have a very large telco company that has been working on the customer acquisition. Okay, this telco usually they, of course, they are involving with the customer every day. So they have the call center. In this call center, they collect data on certain data about whatever customer requirement. Okay, let's say in this telco, we have certain data from the customer, and the data we're going to uh, storage in the data warehouse. Okay, there are some data here, such as call usage, non-call usage, non-call usage charges, 3 months rolling average for usage and billing, customer lifetime value or LTV, customer profitability tier. Okay, these are the metrics lah for every consumer. Okay, for this case study, the telco has received complaint from a number of consumers on drop calls or drop packets. Okay, let's say they want to change their package that they are using. You, for example, you have like you using the Maxis a very expensive package and you want to change it to the affordable one. Okay, that's some sort of example lah. Okay, all these drop calls or drop packages, okay, resulting in revenue leakage and customer attention. Okay, the IT team believe that inspecting the data from the cell phone towers can give them a clue on whether the failure is due to poor infrastructure. The business team also wants to include the data from social media and newsprint about the quality of service, customer sentiments, competitive comparison, and product service review. To process this additional volume of data, the IT team undertook a study on the overall impact the result on which of the followers. So this is the result of the study. So after they receive all the complaints from the customer about the how poor the connection is, the package is too expensive, then the business team also want to use that data to study whether they should improve their their service and everything lah. Okay, so the result from the study of the telco big data, first the current data in data warehouse is 5 terabyte, which is 3 years rolling. New data from towers is 400 megabyte log per day. New data from social media and others is 250 megabyte per day. Content from documents, contracts, and call centers data is 200 megabyte per day. email, forum posts, and social media is 100 megabyte per day. So this is all the data that they discovered, okay, from the data warehouse, from the towers that receiving signals, everything. And for social media, they also get the customer feedback from that platform. And then from the documents, from the emails, that's how big the data is. Okay, that is the result of the study. And then based on the data analysis, the IT team concluded that the database cannot handle the type, volume, and processing complexity of the new data. There are the reasons. So this is the following reason why they cannot handle this type of volume and the complexity of data. First, the data is stored in columns and table structure within database. So to process the data, you need a finite structural definition first, called the data model, and then relationship between different data structures are represented by data. Data manipulation language and data definition language are the two key mechanisms of processing data in the database. Databases are highly optimized for handling finite transactions. Then databases can be abstracted from a physical layer for tuning the architecture. And then databases cannot handle so the data is so big, the database cannot handle the processing of document or semi-structured types of data. Okay, and the last reason is the procedural language or other programming language interfaces on the database add overhead in processing and often end up processing data outside the database, which require the cycle of moving vast amount of data, and the problem will magnify with unstructured and other new data types. Okay, that's a lot of reason there. Okay, to process data other than structured and additional volumes to current data, a combination of heterogeneous technology is recommended. Okay, this is a solution based on the problem listed in the slide before this. Okay, the solution architecture will include the following type of technology. Okay, first we propose to use the Hadoop, NoSQL, or similar data processing platform driven on non-relational and file system based architecture. Okay, all these technologies, Hadoop, NoSQL, we're going to discuss in the next video, in the next chapter. Okay, and then a part of Hadoop, which is MapReduce programming model, will be implemented for managing data processing and transformation. Of course, they are coming in the package Hadoop and MapReduce. And then data discovery and analysis will be implemented using W. All data mirror software that abstract the complexity of MapReduce and works directly on Hadoop for data integration and management. Basically, they are using all this kind of technology that we're going to discuss later. Analytics on Hadoop will be implemented using R, Prediction, or other competing technologies capable to MapReduce integration and management in memory. Data processing solution like ClickView need to be tested further for advanced reporting requirements. Depending on the success and adoption of the new stack of technologies, hardware infrastructure will be running on a commodity platform based on multi-core processor and up to 96 gigabyte. That means it has to upgrade its hardware infrastructure, and then it also has to upgrade this architecture for the new infrastructure, because it will not be based on the storage sharing network, which is the short for storage sharing network is SAN. Okay, but on direct attached storage, for short is DAS. A random configuration will be set up for failover. Okay, so we don't want the redundant configuration. And then a landing zone, which is the first one, the loading data, okay, will be available on the existing server with unlimited storage. The storage will be designed for high capacity and not for high performance. Security for the raw data will be implemented on current disk storage access policy. And lastly, security rules for non-relational data post-processing will follow the existing rules in the LDAP repository. Okay, for the EDW data. Okay, this is all the solution they are proposed. Basically, technology that we're going to discuss in the next chapter, and then upgrade the memory, upgrade the hardware, this architecture, and so on. Okay, for data processing, beside infrastructure, we also can solve the problem by upgrading certain things in data processing. Okay, first, processing of different types of data will be assigned to different clusters of system. Documents and text data will be processing using discovery rules. The result set will be a structured output of text and keywords, occurrences, counts, and processing dates. Then audit, balance, and control will be implemented for tracing data processing across layers. Business rules will be programmatically implemented with MapReduce and other programming language that can scale and perform like Java or Ruby. Okay, all these languages. Okay, number 5. Metadata for data loading and processing will be implemented in file system. A catalog of such metadata will be versioned and stored using version control software. And number 6, the designated software stack such as Karmasphere or Prediction will manage semantic layers for data output from the different dataset and their processes. The rules themselves will be stored in a central repository for source code management. Number 7, all the processing all the pre-processing and processing of data will occur outside the data warehouse. That means it cannot be done inside the data warehouse and other relational data environment. Okay, and then number I lost count already. Okay, 6, 7, 8. The hybrid data processing architecture will provide independent machine software and data scalability across the entire ecosystem. And lastly, any data integration between the new data outputs and the EDW will be done at a metric level using metadata. I know you've seen a lot of these technologies name like Karmasphere, Prediction, and so on. But I think we're going to focus on certain technologies only in the next chapter. Most of our focus is more on the Hadoop technology, of course, and for the non-structure is going to be NoSQL software. Okay, other than that, I'm not sure it will be covered in our syllabus, but we will see in the next video.